Hey everyone, welcome to Physics 40S. This is Lecture 2 of Unit 1. It's Dr. Carroll here. Hope you're having a lovely day. So, here we are in our notes. So we're at Unit 1, Lecture 2. And we are going to look at fit to page. What do I want to do? Fit to width, I think I want to do. There, that's better. Okay, I want to look at kinematic equations because vectors are part of that. And these kinematic equations you should remember from grade 11 physics. Maybe use slightly different symbols, but here we go. So the first is velocity average is v1 plus v2 over 2. Velocity average, if you can get that in a constant acceleration question, that's very helpful, useful information, or even constant velocity. Well, you don't really need to get the average there. It'll be the same as the initial and the final. I use 1s and 2s, sometimes i's and f's, more often 1s and 2s. Delta v, that is our uppercase Greek letter delta, is the change in velocity, so it's v2 minus v1. The displacement delta d is v average delta t, because the average velocity is change in displacement over change in time. So you could also write it as, I better put brackets around it, v1 plus v2 divided by 2 times delta t. There we have v average is delta d over delta t. I don't always put in the arrows, sometimes I forget. You'll get it. Constant acceleration questions. Change in velocity over change in time. So v2 minus v1 over t. If I cross multiply, I get v2 equals v1 plus a delta t. And then 2 that we get from graphical ways. Delta d is v1 delta t plus 1/2 a delta t squared, or v2 squared is v1 squared plus 2a delta d. Those ones I try not to use as often as the other ones, but they still creep in. I find that these kinematic equations, getting the average velocity, even if you aren't asked for it, helps with everything else. There are questions you may remember where you had to do the quadratic. Well, we're going to be able to avoid the quadratic often by using the average. So we aren't going to use quadratic equations to solve any of the questions that we're looking at. Okay, so let's try a few examples. Here we go. Let's say Nicole, I'm not sure if there's a Nicole in this class, but if there is, let's say Nicole is driving a silver car at 20 meters per second. Then she decides to accelerate, so she's covering the next 750 meters in 30 seconds. So we're going to calculate the acceleration, the final velocity, and let's also calculate the average velocity. I'll throw that in too. And I'm not going to use the vector arrows here. I'm going to assume going east is positive, so I won't use the vector arrows unless I really have to. So any problem solving, you make a list of what you know and what you got to find. So our initial velocity is 20 meters per second. Our displacement is 750 meters, covering that in 30 seconds. So we're going to get the final velocity, the acceleration, and the average velocity. So the average velocity is delta d over delta t, 750 meters in 30 seconds, so 25 meters per second. Now we started at 20 meters per second, we're going to 25, so our final has to be 30. If you can't do that so quickly, then just plug in the numbers, okay? So we're going to plug in, so get 2v average minus v1 equals v2. So v2 is 2 times 25, which is 50, minus the speed, which you started with, 20. So you have 30 meters per second. Here I'm saying speed and velocity, the same thing, assuming straight line going east or to the right. So now I know v2 is 30 meters per second. I know v average is 25 meters per second. And I can get the acceleration, which is the change in velocity over the change in time. So 30 minus 20, which is 10 divided by 30, 1 over 3.33 meters per second squared. Sometimes you'll see it written as meters per second per second. Other units of acceleration, you sometimes see kilometers per hour per second. I'm not going to use that one very often. I like to write it meters seconds to the minus 2. That's a quicker way of writing meters per second squared. Okay, so that was one example. Now, just when I said I wouldn't care about vectors, here's an example where we'll look at vectors. So in question 2a, an airplane flying north at 160 meters per second changes its velocity by 80 meters per second. calculate the final velocity. So the change in velocity is v final minus v initial. So v final is delta v plus v initial. Change in velocity is delta v. 80. I leave off the units. Sometimes people do that, leave off the units until the end and they put it in just to prevent things from cluttering up. So I'll do that here. So I go 80 meters per second east plus 160 going north. So I got 80 east and then 160 north. I add those as vectors. These are nice. I don't need some fancy vector collector because these already are legs of a right angle triangle. And so we're going to get v final is 80 squared plus 160 squared. Take the square roots. And I'm going to double check that here. 80 squared plus 160 squared. Take the square root. 81 point. Why do we say 178.79? That's interesting. Let's try it again. 80 squared plus 160 squared. Take the square root. 178.89. There we go. Meters per second, and then we're going east 63.43 degrees north. So to get that angle theta, we're going to take the inverse tangent of 2, because 2 is 160 over 80. 2 inverse tangent on my calculator. There we go, 63.43 degrees. Okay, so that is my final velocity. So you can think of the 80 meters per second east has the wind, and it is knocking the plane off course. So on course, you'd have online computers every nanosecond, whatever, to keep things going smoothly. If that process took 45 seconds, calculate the acceleration. Remember, acceleration is change in velocity over change in time. The change in velocity could be magnitude, could be direction, could be both. Okay, any of those are changes in velocity giving you acceleration. So our change in velocity was given as 80 meters per second east divided by 45 seconds given, so 1.78 meters per second squared to the east. Okay, so that's an airplane example. Let's continue on here. Let's say some vehicle was going 50 meters per second south, and then later on it was going 12 meters per second west, so it turned from south to west. We want to get the change in velocity. So the change in velocity is v final minus v initial, which is the same as v final plus negative v initial. So v final is 12 meters per second west plus 50 meters per second north, right? North is the opposite of south. So we don't subtract vectors, we add the opposites. So 12 meters per second west plus 50 meters per second north. So I'm going to get delta V, use the Pythagorean theorem, 19.21 meters per second west, 51.34 degrees north. So that is my change in velocity. Okay? Let's look at a fourth example. A jet, maybe a Winnipeg jet, is going at 100 meters per second, accelerating at 8 meters per second squared. Fine, let me write it like this. Then it goes at 180 meters per second. Calculate delta D and delta T, and let's always calculate V average, or try to anyways. So V1 is 100, that is given. V2 is 180, that is given. Acceleration 8 meters per second squared, that's given. Delta V, well I can do that in my head, right? 180 minus 100, so it's 80. So V average is V1, 100, plus V2, 180, so that's 280 divided by 2, so 140 meters per second. And then how long did that take? Well, let's see. Acceleration is change in velocity, 80 over time. I don't know the time, but I do know that the acceleration is 8. So 8 is 80 over time, so time is 80 over 8. Which is 10 seconds. So it took 10 seconds for this jet to accelerate. Maybe it was a toy jet, I'm not sure. Or some secret jet that we don't know anything about. And then the delta D is V average delta T. V average is 140 times 10, so 1400 seconds. So I did have to get the time first to get delta D. And this is a point about questions. You don't always have to get the answers in the order in which they're listed. Sometimes it's helpful to get the delta T before the delta D. Okay, so beware of that. Sometimes it's more helpful, like I said, to get something listed third before the second or the first one are listed. Just get the right answers, right? Okay, let's talk about a rocket. Maybe a Houston rocket reaches a speed of 628 kilometers per hour from rest in 3.72 seconds. Calculate delta D and A, and let's also get V average as well. So V1 is 0 meters per second. That's when we're at rest. V2 is 628 kilometers per hour, but all this other stuff's in seconds. So remember, to go from kilometers per hour to meters per second, you divide by 3.6. So the meters per second equivalent is always going to be smaller than the kilometers per hour equivalent. So V1 is 0, V2 is 174.44. It took 3.72 seconds. So delta D is V average delta T. V average is 0 plus 174.44 divided by 2, which I didn't actually get that number, did I? 174.44 divided by 2, 87.22 meters per second. Okay, so then delta D is V average delta T. So 87.22 times 3.72, and you get 324.46 meters. And the acceleration is the change in velocity over change in time. So our change in velocity was 174.44 over 3.72 seconds. So this rocket's accelerating pretty fast, large number, 46.89 meters per second squared. Okay. Let's go on here and talk about airbags. They're important parts in vehicles. We want to calculate the acceleration of an airbag that deploys. So it is going to inflate in 30 milliseconds, which is 30 by 10 to the minus 3, or 3 by 10 to the minus 2, or 0.03 seconds. And it moves out 40 centimeters, so delta D is 0.4 meters. Here I'm making some metric conversions. On the fly, also calculate V2, and we'll get V average as well. So V1 is 0. It's like the material, the fabric, isn't moving relative to the observer, who's, I guess you could say, would be, let's see, outside the car. And then it expands out 0.4 meters in 30 milliseconds. So my average velocity is 0.4 out of 0.03, 13.33 meters per second. And remember, average velocity is delta D over delta T, but it's also V1 plus V2 over 2. So V2 is 2 times 13.33 minus V1, which was 0, so 26.66 meters per second. That's V2. Delta V is 26.66 minus 0, which is still 26.66. And we divide by delta T, which is 0.03. So 26.66 divided by 0.03 is 888.67 meters per second squared. Okay, and we got the average before, 13.33 meters per second. Okay, any questions? Send me an email. Okay, we're going to have a worksheet with lots of these coming up soon. Let's say you're a runner, which I'm not, and you're running at 3 meters per second, and you accelerate at 0.2 meters per second. Delta D is 12 meters, acceleration 0.2 meters per second squared. Calculate delta T and V2 and V average. So here, let's see. Let me try to do it a different way here. Let's just try that. V1 is 3. A is 0.2. Delta D is 12. V2 is V1 plus A delta T. No, I don't have that one. V average is V1 plus V2 over 2, or delta D over delta T. No, I can't do all those, so I'm going to have to use V2 squared is V1 squared plus 2A delta D. So V2 is the square root of V1 squared plus 2A delta D. Now, somebody's going to say, do I do positive square root or negative square root? Well, here let's use positive square root, okay? We just assume we're going to the right as positive, and that'll work. So it becomes the square root, and I already have it written there, don't I? 3 squared plus 2 times 0.2 times 12, and I get 3.71 meters per second. So that's V2. V average, I can get that. V1, 3 plus V2, 3 plus 3.71 over 2. So 6.71 over 2. 6.71 divided by 2. 3.36, close enough, meters per second. Okay, and now to get delta T, well, you can do it two ways here. I could just use this equation. V2 is V1 plus A delta T. So delta T is delta V over A. And you get 3.55 seconds. Or now that I know what V average is, I know that V average, 3.36, is delta D, 12 over delta T. So delta T is 12 divided by 3.36, and I get 3.57 seconds. So we're just rounding off a bit. Close enough. I couldn't tell the difference. I bet you couldn't either. So we have, maybe you could. So either of those methods will work. Okay, so we're talking about acceleration in question 7 of just a runner. Has the runner increases speed and has good technique. Maybe had an energy bar before the big race. But there's another kind of acceleration that the kinematic equations can be helpful with, and that is acceleration due to gravity. And on the Earth's surface to 1 decimal place, the acceleration due to gravity is 9.8 meters per second squared. We will see that that is the same as a Newton per kilogram a little later on, and we're also going to look at gravity in more detail later on, because the Earth is actually squashed in the poles here, so the gravity is a bit more in the poles than it is along the equator. And when you launch satellites, that's actually an important thing to deal with. But for now, to 1 decimal place, 9.8 meters per second squared at the Earth's surface. So suppose we had a object and it had 0 meters per second, so we're just dropping it from somewhere. And so when you see 0 meters per second in a drop kind of question, don't worry about this page number, just get rid of that. Acceleration due to gravity, sometimes just called g, you want to call it ag, go ahead, minus 9.8 meters per second squared. So I'm going to assume going down is negative. Delta D is minus 3.5, so it fell 3.5 meters. I think this question is actually an apple falling from a tree, sort of that Isaac Newton thing. So the apple falls 3.5 meters, doesn't fall far from the tree. We'll get V2 delta T, and let's also get V average. Okay, so V average is V1 plus V2 over 2. Now we don't have enough information for that. Delta D over delta T, not enough information for that. So we got to use this one here. V2 squared is V1 squared plus 2A delta D. So V2 is the square root of 0 squared plus 2 times negative 9.8 times negative 3.5. Remember, you have to take a square root of a positive number. If you're starting to take square root of negative numbers, something weird is going on right now. Later on in physics, you will do that with imaginary numbers, but for now, no. So V2 is negative 8.28 meters per second. So that just means that the apple has fallen to the bottom of the tree and has now picked up speed from 0 to 8.28 meters per second. How long did it take? Delta T is delta V over A. So 8.28 minus 0 over 9.8, the negatives cancel. It took 0.84 seconds. V average, V1 plus V2 over 2, so 8.28 over 2, I guess negative, Can I do that in my head? Negative 4.14. Double it. 8 to, yeah, meters per second. So that's just dropping an apple from a tree 3.5 meters high. What if we drop something from a lot higher distance here? Here we have a object at the top of the CN tower, which is 550 meters high, and we drop it. And so the acceleration minus 9.8 meters per second squared. We're having a displacement of 553 meters negative. It's dropping it. We aren't throwing it down. We're just dropping it. So V1 is 0. So V2, we want to solve for. Delta T we want to solve for. And so how can we do that? V average, let's get that too somewhere. Actually, let's not bother with that here because there's two points to this. Or I'll do it later. So let's see. Let's use an equation we haven't used yet, just for some variety here. So if the displacement is V1 delta t plus 1/2 a delta t squared, and it's at rest, then this term vanishes. So it can isolate for delta t, so it's 2 delta d over a, but I take the square root. So 2 times 553 over 9.8, and you see that it takes 10.62 seconds. You also see that if, I got rid of the negative signs, fine. If we were dropping at a greater distance, well, it would take more time, right? Because the delta d is in the numerator here. It's not directly proportional. There's a square root factor. But the longer you're falling, the longer you're in the air. I mean, that hopefully is common sense. So it takes 10.62 seconds for that object to fall to the bottom. And I'm not talking about terminal velocities or air resistances or frictions or all this other stuff. Just in a perfect idealized situation, this is what you would have. And so my final speed would be just before it hits the bottom. Don't say 0, but just before it hits the bottom. So V2 is V1 0 plus negative 9.8 times 10.62, which should be 104.08 meters per second. If I really wanted the average velocity, it would be negative 104.08 plus 0, all that divided by 2. So that's going really fast in theory. Okay. Then remember there was a question where it said, what's the speed at the halfway point? I saw that in a book somewhere, and I said, that's not a good question, because are we talking about the halfway point with respect to distance covered or with respect to time? So if I ask you a question like that, I'll be more specific. So I could say with respect to WRT, that is short for with respect to. So with respect to distance, calculate V2 at the halfway point. So we have here V2 squared is V1 squared plus 2 times negative 9.8, and it would just be 553 divided by 2. Okay, and you'd get 73.6 meters per second. I'll put a negative sign there. So you see that it's more than half of the velocity when it hits the ground. And that's just the way the mathematics works. That is science. It's not half, it's more than half. And the time needed to get to the cover half the distance, well, you'd be going 73.6 minus 0 over 9.8, 7.5 seconds. So that's more than the time, sorry, it's more than half of the time needed to go the full distance. So 7.5 meters per second. Okay? Here we have a question where you throw something into the air like you just don't care. So let's say your initial speed is 4 meters per second. You throw it in the air, and so the velocity decreases because now you're fighting gravity, trying to defy gravity. Goes to 0, and then of course it would start to fall again. So we want to get delta D and delta T. V average I could get, it's 2, right? It's 4 plus 0 over 2. The average is 2 meters per second. Okay, so how high does it go? How long does it take? How high? That would be my displacement. So if I want to use this equation, delta D is V2 squared minus V1 squared over 2A. v2 squared. So it stops. So 0 squared minus 4 squared over 2 times minus 9.8. All the negative signs take care of themselves, and you get 0.82 meters. So the object goes 0.82 meters up before it starts to fall down. How long does it take? Delta V is 0 minus 4 over acceleration negative 9.8. So 4 over 9, 0.41 seconds. That's an S, seconds. How long would it take the arrow to hit the ground? Well, if it's 0.41 seconds to go up, another 0.41 seconds to go down. So it'll be twice that, 0.82 seconds. You can convince yourself of that. Do it. Okay, here's a question. A car is slowing down. This is important. We think of acceleration usually as increasing, but you could have a deceleration, which is a negative acceleration in magnitude, not turning. This is also all the stuff you remember from the graphs from last year where you like switch direction, and there's all these different possibilities. Here we're just slowing down at a rate of 20 kilometers per hour per second. Oh really, I did that? Well, let's convert that. So I'm going to divide by 3.6, and instead of 20 kilometers per hour per second, it's going to be 5.56 meters per second How far does it travel? Its original velocity is 50 kilometers per hour, so I'm going to convert that to meters per second by dividing by 3.6, right? Remember, you divide by 3.6. And the final velocity is 5 meters per second. Okay, so this question here is not using gravity. Don't always think that we're talking about acceleration due to gravity. Here, because of the normal force, if we're assuming we're on a straight level surface here, we don't care about gravity. Okay? It's canceled out by the normal force, the gravitational force. So V average would just be 18.89 over 2 if I wanted to do that. But it seems we're getting some practice with these other equations, which is good. Got to have practice with all sorts of things. So delta D is V2 squared minus V1 squared over 2A. So 5 squared minus 13.89 squared over 2 times, where does negative 5.56 come from? Oh, that's right, that's the acceleration. So the car is slowing down to 5 meters per second. It took 15.10 meters. These are known as, well, if it stopped, it would be a stopping distance. Some of you are taking driver's ed with Murray or whoever it is, and you learn all about stopping distances and why you shouldn't drive so fast. And all about friction and surfaces like that. And then the delta T is delta V over A. So V2, what's V2, my final? You have 15 there. That's not 15, that's 5. That's not a 15, that's a 5. 5 minus 13.89, so minus 8 over, yeah. That's 8.89 divided by minus 5.56, which was the acceleration in units of meters per second squared. So I get 1.6 seconds. So be careful with the units, right? Kilometers per hour per second, convert that to meters per second per second. So the stop, it was not a stopping time. It didn't go to 0, sorry. But the slowing down time to 5 meters per second took 1.6 seconds. Okay. I thought this was a short unit. I'm gonna give you an assignment, and we're gonna practice it. And that's really the story for Unit 1. Okay. So let's have a stopping force right here. Have fun.